We've spent a few videos on descriptive statistics, visualizations of data. We now want to move on to the first piece of inferential statistics, which is regression. This video will introduce the idea of linear regression, which is the goal being to understand the concept and in particular the coefficients. Here is a scatter plot of two numeric variables in a data set about possums. The variables are the length of the whole animal, including the long tail in centimeters, and the length of just the head in millimeters. As usual, the dots are cases, representing the measurements of one specific possum. As before, a natural question in a scatter plot is this: is there a relationship between the two numeric variables? In this scatter plot, it looks like there might be a positive correlation. This also intuitively makes some sense. The larger animals can be reasonably expected to also have larger heads. What is this relationship? It's always hard to say, but statistics tries to guess. And the first guess is the simplest relationship, a linear relationship. This is a relationship represented by a straight line. So let me briefly review lines. A couple videos ago, I mentioned that logarithms were an important piece of mathematical background that was worth reviewing. Equations of lines are another such piece. The standard form is this, called the slope-intercept form, and I hope that this is at least a little familiar. X and y are the coordinates, of course, and the line is then described by two numbers, m, the slope, and b, the y-intercept. The y-intercept is the less important for today's interpretation, though it certainly carries meaning. You can think of it as where the relationship starts. When x, the input, is 0, the output is the intercept b. The slope is the more important measure. It tells how quickly the line rises or falls if the slope is negative. A linear relationship is defined by its slope. A steep slope means that changes in x correspond to large changes in y, and a shallow slope means the opposite. So let's try to fit a line to this scatter plot. Regression is the mathematical task of matching a function to a collection of data. Linear regression is matching a linear function. That is, trying to draw a line that best captures the data. I'll draw this line. What line have I drawn? Well, here's an equation for the linear regression generated from this data. Note two things, the intercept and the slope. The intercept is 41, which is not terribly relevant here, but the slope is very useful. It describes the relationship. For every centimeter of length, the head of the possum increases by 0.59 millimeters. The slope is in many ways the relationship. Notice the hat over the y. This is a notational reminder that this y is an approximation. Not all the data fits the line perfectly, of course. This y-hat notation is a useful reminder that this y is not the perfect outcome, but just a statistical approximation. This is a linear regression then, a line meant to fit the data. It can then be used to make predictions. If I put a body length into the equation of the line, say 90 centimeters, then the linear regression predicts a 94.1 millimeter long head, and these predictions can then be compared against future data. Obviously, the line is an approximation. For each data point, I can ask how far it is away from the line. This is called the residual. Each data point has a residual with respect to the linear regression. For this first data point, if I put x equals 75 into the line, it predicts 85.25 millimeters. But the actual value of this particular point is 84.7. The difference, y minus y hat, is the residual for this data point. And in this case, the residual is negative 0.55, showing that the data is 0.55 millimeters below the line. Now, how was the linear regression determined? This is actually quite a difficult mathematical problem, and one we'll mostly leave to the statistical software. However, I want to give you a rough outline and introduce an important term. The residual is the difference between the data point, and the line. There is one residual for each data point, for each case. If I number the data from 1 to n being the number of cases, then I have all these residuals. Well, then I can make this expression, the sum of the squares of all the residuals. How is the line chosen? It is chosen to make this number as small as possible. This is called the least squares regression. It is the line for which the sum of the squares of the residuals is minimized. Actually, doing the minimization is quite complicated, but you should at least understand the decision criteria. Why do we square the residuals? Well, there are several reasons. One is that it makes everything positive, since it's not important whether the data is above or below the line, just how far away it is. Second is that it emphasizes large distances. If there are any large residuals, they will have an even larger impact on this when the sum is squared, so that these large residuals will be discouraged in the method of least squares. There are other reasons as well, which I won't get into now, but which have to do with the mathematical notions of length and optimization strategies. That's the idea of linear regression, the importance of the slope, and the least squares method. For the rest of this video, I want to give a short idea of where else we can go with this method. I can bring more variables to bear on this analysis. This dataset also includes the age of the possum, as well as the sex. Here is the scatter plot color-coded by the sex variable, red for male and blue for female. The males have on average slightly larger heads for the same body lengths. I've drawn linear regression separately for the male and female possums. What's going on with these two lines? Well, the first linear regression was a line y hat that depended on x, the body length. Maybe y hat depends on more. Maybe it depends also on the age and sex variables. I can extend this linear regression with more terms that all look like the slope of a line, a constant times an input variable. This model then says that the head size is determined by the length, the age, and the sex, with these coefficients describing the relationship. Also, sex is a categorical variable, so to put it in an equation, I need to make it a number. I'll choose to make male to be 0 and female to be 1. Doing this makes it something we call an indicator variable, or sometimes a dummy variable. By making male set to 1 and male set to 0 and female to 1, this term, which makes all the head sizes 1.66 millimeters smaller, only applies to the female possums. For the male, this would be multiplication by 0, which removes this term entirely. It wouldn't do anything. Here are the two lines again on the separated scatter plot. Ignoring age for now, I can give a good interpretation visually for what this indicator variable is doing. This negative 1.66 is just shifting this line by 1.66 units down. The female line has the same slope, just slightly lower, 1.66 millimeters lower exactly under the male line. For indicator variables, where each category is arbitrarily set to a number, I can view the results as shifts of the line up or down. And the point here is threefold. First, there is mathematics to create linear regression by the least squares method, finding the best line by minimizing the residuals. Second, the numbers in that line carry statistical meaning. They encode the relationship between the data, at least approximately. Finally, those relationships can be extended to more variables. Extending to other numeric variables is just adding new terms to the equation, but to use categorical variables, we have to assign numbers to them, making them indicator variables. In all of this, the coefficients carry the meaning of the relationship between the data.